Hi students. In this lecture, I am going to discuss rolling motion. Let us see. So you can see it is a combination of translation and rotation. For example, if you take a wheel of a vehicle, it is a translating and rotating. So combination of these two is called a rolling motion. So it is, suppose this is now a body or you can say wheel, which is now rolling. If you take only translation, then each and every point in that body having same velocity, same acceleration, and same displacement. That means we can replace the entire body with a single point, that is center of mass. Suppose velocity is vcm. That means for all points, velocity is now vcm. Same magnitude, same direction. Okay. Next, if we consider pure rotation, that means axis of rotation is fixed. Then, except the points on the axis of rotation, all points follow circular path. See, it is the rotation like this. Suppose omega is the angular velocity. Then each and every point in that body, except the points on axis of rotation, follow circular path. So if you take now, suppose take a point on circumference. For this point, velocity because of rotation, it will be r omega. And you can see for this point, it is velocity r omega vertically downwards. And for the bottommost point, velocity r omega like this. And for this point, velocity vertically up. So except the points on axis of rotation, remaining all points are following circular path. So combining these two, that is called rolling. It is rolling motion. Now in this, we discuss rolling without slipping. Okay. For example, there is a plank. This is a plank which has velocity v. We are keeping our body which is rolling on the plank. So keeping a body which is rolling on the plank. So this is rolling on the plank. See, for this, for contact point velocity, if we assume that Vcm is greater than r omega, for contact point velocity will be Vcm minus r omega. If velocity of the contact point is the same as that of contact surface, then there is no slipping. I am repeating, velocity of the contact point and that of the contact surface both are same, then there is no slipping. Then it is called rolling without slipping. Or we are saying pure rolling. So condition is here. Velocity of the contact point Vcm minus r omega is equal to V. This is the condition for rolling without slipping. For example, in this diagram, for the plank, velocity is left side. I will make diagram here. For the plank, suppose velocity is left side. Then see the condition for without slipping rolling. Condition for that. So if you take for the plan, velocity left side, then for contact point velocity, it is r omega minus vcm. So condition is now r omega minus vcm is equal to v. This is a condition for rolling without slipping. So a key point is that velocity of contact point should be same as that of the contact surface. Okay, condition is like this. Okay, for example, this body is now rolling on ground. So rolling on ground means for ground velocity equal to 0. That means writing in the place of v it is 0. Then see what happens. It is vcm minus r omega, or you can write r omega minus vcm equal to 0. That implies vcm is equal to r omega. So this is when velocity of the contact surface is 0. Okay. But remember, in this case, even though for contact point velocity is 0, but for contact point acceleration is not 0. Okay. Let us now focus very carefully. So now we are focusing acceleration of the contact point. So when you want to find out acceleration, so we have to focus because of translation, what is acceleration? Because of rotation, what is acceleration? So you can see here, because of translation, for each and every point, acceleration is the same. That is ACM. It is now ACM. So for this point also, acceleration is AC. For any point, same because of translation. Now, because of rotation, when body is rotating, except the points on axis of rotation, remaining all points are following now circular path, right? So because of circular motion, it has acceleration and that has two components. One is centripetal acceleration, one component, and one is suppose this is now sense of rotation. Okay, that means I'm taking it alpha is now clockwise. Okay, when alpha is a clockwise, tangential acceleration will be it is r alpha. So here omega may be clockwise or omega anti-clockwise. That is not important. We have to focus direction of alpha. Direction of alpha is in this diagram clockwise. Therefore, r alpha will be left side. So what we are doing here, because of translation, for each and every point, acceleration is ACM that we have taken for contact point. Next, contact point is a following circular path about center of the body because body is now rotating. So because of that, it has two components for acceleration. AC towards the center, R alpha that is along the tangent, right? Now see carefully here. So here we got BCM minus R omega equal to 0, right? Now if we differentiate that, we get ACM minus R alpha equal to 0. That means ACM is balanced by R alpha, but still AC is present. That means for contact point, even though velocity is 0, but acceleration is not 0. It is centripetal acceleration, which is towards center of the body, or you can say towards axis of rotation. Okay, let us see regarding this important points. Let's say first point, pure rolling or rolling without slip. Velocity of the contact point is the same as that of the contact surface. If a body rolls without slipping on ground, then velocity of contact point is zero, but acceleration is non-zero. It is toward the center, which is nothing but centripetal acceleration. Next, so remind these 2 points we have to discuss. Okay, rolling frictional force acting on the body may be zero or non-zero, and it is static. So which we are going to discuss. And next point, the path of a point on the circumference is a cycloid, and the distance moved by that point in one full rotation is 8r. Okay, so we can discuss these 2 points. Let us focus the last point regarding cycloid. First focus here, rolling. So VCM, and because of rotation, we can see for contact point, velocity will be, it is r omega, that is left side, and this is VCM right side. If r omega is less than VCM, means for contact point, velocity is now right side. Okay. If VCM is less than, sorry, if r omega less than VCM, for contact point, velocity is now net value right side. That means contact point is having velocity with respect to contact surface. That means it is now slipping. And this is now slipping forward. This is known as a forward slipping. So I'm writing in brackets of forward slipping. Because for contact point, net velocity is forward. This is known as a forward slip. If r omega is greater than VCM, that means for contact point, velocity is now left side, net value. So this is known as backward slipping. It is known as backward slipping. Okay. If r omega is equal to VCM, remember here we are taking rolling on ground. Okay. Rolling on ground. So r omega equal to VCM. No slipping. So for contact point, there is no velocity. That means frictional force. It may be zero or maybe non-zero. Since there is no slipping, friction will be static. Okay. We are going to solve questions based on this point, means how to calculate frictional force acting on the body. So here r omega equal to VCM. So we have taken body is rolling on ground. I am writing here. It is rolling on ground. Or you can say for contact surface, there is no velocity, right? Now see in this, distance moved by center of mass during one rotation. Okay. If we consider VCM is a constant, okay. If VCM constant, then see what we can write. Displacement of center of mass is equal to VCM into time taken to complete one rotation. So here we have taken VCM is a constant. Then see what we get. It is equal to VCM into, in the place of t, we can write 2 pi by omega. In the place of VCM, see what we can write. VCM equal to r omega means no slipping. If you take no slipping, this is r omega into 2 pi by omega. It is a 2 pi r. So it covers a distance, or you can say displacement equal to 2 pi r if there is no slipping. Okay. If slipping is there, then see what happens. There is no change. The time taken to complete one rotation, that is 2 pi by omega. If VCM is greater than r omega, okay, I'm writing here. If VCM is greater than r omega, this is greater than r omega, then this value will be greater than 2 pi r. That is a forward slipping. If you take backward slipping, displacement, or you can say distance traveled by center of mass will be less than 2 pi r. So in backward slipping less than 2 pi r, forward slipping greater than 2 pi r, no slipping 2 pi r. So here we have taken velocity of center of mass is a constant, means ACM equal to 0. Okay, right. Now focus carefully. If we consider a point on circumference, so we are saying that, well, the path of a point on circumference follows, it is known as cycloid. That path name is cycloid. So we are taking a point on circumference. Let us set time t equal to 0. It was in contact with the ground. After some time, this point will be somewhere here. Suppose this is a theta. This is now location of same point. Now you can see its velocity. Because of translation, it is VCM. Because of translation, it is VCM. Suppose it is right side, VCM. So VCM right side. And this is R omega. And since we are taking rolling without slipping, R omega equal to VCM because rolling on ground. So you have to keep in mind, I'm taking here rolling on ground. That's why VCM equal to R omega. Now you can see between these 2 points, what is angle? If I extend like this angle is also same, right? Theta only. Means between VCM and R omega, angle is now 180 minus theta. You can see carefully. It is 180 minus theta. See now what is resultant? Resultant is now 2 VCM cos of 180 minus theta by 2. So we have learned in vectors that if we have two vectors of same magnitude, angle between them is theta, then resultant of those two, 2 into magnitude of that vector into cos of the angle by 2. So I have taken same cos of the angle by 2. So this is now how much? 2 VCM sine theta by 2, right? Sine theta by 2. So now we want to calculate distance traveled by this point during one rotation. Distance traveled by this point during one rotation. Then see. So here you can see speed. Speed is not a constant. Speed is a keep on changing. So since speed is a keep on changing, we are taking a small time interval dt. So we calculate now in that small time interval dt distance traveled. Like this, we take small time intervals from t equal to 0 to till this point reaching ground. Okay. Then see distance traveled in a small time interval dt, that is now ds, which is equal to v into dt. Okay. Now we have to integrate. Then see what we get. 2 VCM sine theta by 2, or in the place of theta I can write omega t by 2. So you have to keep in mind we are taking VCM is a constant. Okay, then only omega constant. When omega constant, we can write theta equal to omega t, right? Into dt. Now take limits 0 to t. Means we are focused now one time period. That means we are taking when t equal to 0, it is touching the ground. When t equal to capital T, it again touches the ground, right? Now see calculation part. 2 VCM. In the place of VCM, I can write R omega. Integration of sine theta d theta. It becomes minus cos omega t by 2 upon omega by 2, right? Now take limits 0 to t. 2 comes here, it becomes a 4. Omega is cancelled, 4r. Having here minus cos omega t by 2. Take now upper limit. It becomes cos pi minus 1. Take lower limit. It is 1. This value is now 2. So this is now equal to 8r. So length of the path followed by a point on circumference during one rotation is 8r. And that path name is a cycloid. Okay. We can see diagram once here. So first it is somewhere here. During the entire motion, center of mass will be at same height. No change in that. And center of mass follows straight line path. And we are taking a point on circumference at one point of time somewhere here. And again finally comes to contact point. So it is now like this. This is known as cycloid. Okay, its length in one time period is 8r, right? So here one thing we have to keep in mind, calculation of velocity and acceleration for each and every point. So when we are taking velocity or acceleration, we have to focus separately because of translation and because of rotation. Just now we have seen while taking velocity, VCM, next R omega. In the same way, coming to acceleration also, so we have to focus because of translation. For example, I am taking one point, suppose somewhere here, distance equal to small r, it is small r. You can see acceleration because of translation, it is if I am taking r alpha like this, sorry, alpha is now suppose clockwise. Because of translation, this point having ACM like this, ACM. Because of rotation, you can see this point follows now circular path like this. Okay. Now, because of circular motion, it is having for acceleration two components. One is along the tangent. So one is along the tangent that is now like this. That is R into alpha. Okay. And one is towards center, that is centripetal acceleration. One is towards center, that is centripetal acceleration. That is, we can say R omega square or it is V square by R. So you can see here ACM because of a translation, R alpha along the tangent, R omega square, or it is V square by R towards the center. Resultant of these three gives acceleration of that point. So whenever we want to calculate acceleration or velocity for any point, so we have to focus separately because of translation, what is velocity or what is acceleration? Because of rotation, what is velocity or what is acceleration? Then take now sum of the vectors, right? So we can expect many questions basing on calculation of velocity and acceleration, right? So you can still remind 2 points here. In pure rolling, frictional force acting on the body may be zero or non-zero, and it is static. In fact, we are going to solve questions basing on this point. You will get a more clarity. And the last point, the path of a point on the circumference is cycloid, and the distance moved by that point in one full rotation is 8r. So here we have taken that VCM is a constant, right?